Today we want to continue the analysis that we and the example that we started last time. So yeah, the technique, we examined multiple techniques last time with a specific example. We we did superposition, and before that we did loop analysis or mesh analysis, and then before that we did nodal analysis. Okay, and then I think, yeah, we did, no, that's a different problem, I think. Okay, so we did nodal, mesh, or loop analysis, and then finally we did superposition, and then we started working on what's called the source exchange method. So we looked at the circuit, we exchanged this parallel impedance and current source into a voltage and impedance. And then after that, after we did that, we summed up the voltage sources, and we ended up with this voltage source and impedance. We turned it back into a current source with an impedance in parallel, and then we used the current divider equation to do the find IO. So all that remains is for us to just calculate this. I mean, we did this, I think, where we find the parallel of this. So this is their product over their sum. So J cancels. I end up with, this is going to be 1 squared plus 1 squared, which is 2 over 2, 1 ohms. So this whole term becomes 1. This whole term becomes 1. So it's 1 over 2, right? So IO becomes half 6 plus 2, 1 plus J over 1 plus J. Okay, so that equals 3 plus 1 plus J over 1 plus J, which is 4 plus J over 1 plus J, right? And then all we have to do is just convert this, divide by 1 plus J, so I end up with 4 plus J over 1 plus J, 1 minus J over 1 minus J, so I end up with 2, and then here I have 4 plus 1, 5, right? 4 plus plus J times minus J is 1, so that's 5, and then plus J minus 4J, that's minus 3J, that's 2.5 minus 1.5 J, and then what we can do is we can convert this into polar coordinates. When we do that, we get we get the same result that we expect, because we remember we solved this problem multiple times. So 2.9156 with an angle of minus 30 something, 30.964, minus 30.964. So the next, so this is as far as this method is concerned. The next method has to do with Thevenin's theorems. So this is method 4 and then 5, 6. So method 5, which is Thevenin. Theorem. And how do we do that? So let me draw the circuit again. So I have 1J, 1 minus J, and then 1, and then 2 and 6. By now I memorized the circuit. So this is resistor 1, J, 2, and then 6 volts, then another 1 ohms, and then 1, and then the capacitor, which is minus J. So the idea is that I want to find the equivalent circuit with respect to those two nodes. So looking up from those two nodes, I want to reduce everything except this resistor into its equivalent Thevenin circuit, right? And then use that to find I/O. So if I take the resistor out, right? That's how you find I need to find plus VOC, the open circuit, and then I need to find Z Thevenin, looking from those two ports. Okay, so that's how you construct the Thevenin equivalent. So I have V Thevenin, and then I have whatever Z7. I'm drawing it as a box because it could be a complex impedance. It could have a complex component, right? And then the 1 ohm is there, and then I calculate. That allows me to calculate I/O. Allows me to calculate what I/O is. Okay, so how do we go about finding the Thevenin equivalent? Well, the first step is we need to find what is the voltage across those two nodes, right? And I mean, again, there are many ways of doing that. There are many ways of doing that. What we could do is we could reapply. We can look at this circuit and apply the source exchange here to get a voltage source, and then we can easily combine the voltage sources and then apply a voltage divider to get VOC. So that kind of simplifies the analysis a bit. I don't have to do nodal analysis again. So if I do that, if I apply source control, source exchange here, I end up again with 2 times the impedance, 1 plus J volts, right? And then the impedance is again 1 and J. Resistor and inductor, and then I have the voltage, and then 1 ohms, and then minus J, and then this is the VOC I'm trying to find, or we can call it V Thevenin, right? So let's apply the voltage divider. In this case, V Thevenin is going to equal, it's the voltage across this impedance, right? So it's going to be 1 minus J over the total impedance, which is 1 minus J plus 1 plus J, right? Times the voltage. What's the voltage in this case? The voltage in this case is going to be 6 plus 2, 1 plus J. I have to sum up this voltage source and this voltage source to get the total voltage source. Okay, so this kind of simplifies nicely. I end up with J cancels with J. I have a 2 here, so I end up with 1 minus J multiplied by, I have a 2, so this becomes 3 plus 1 plus J. So this becomes 1 minus J times 4 plus J. I can calculate this. So this is 1 times 4 is 4, plus 1, 5. I'm getting a similar result. And then minus 4J plus 1J, it's going to be minus 3J, right? Remember, we got this, I think, yeah, but there's a 2. But 5 minus 3J over 2 is what gives us the final result. So if this analysis is correct, we should expect soon to have some kind of divide by 2. Okay, so this is V Thevenin. What about now Z7 and Z7, and how do you find it? You just kill the sources. So you short the voltage source, you open the current source, and then you look at what's remaining. So Z7N. So I killed the voltage source. So I have 1 minus J. In parallel with it, on the other side, I have 1 plus J. 1 plus J. Aha, so this is again, it's going to be 1 minus J parallel 1 plus J. We've already done this. This is 1 minus J, 1 plus J over 1 minus J plus 1 plus J. So this becomes 1 squared plus 1 squared 2 over 2. So this V7N is 1 and it's real, so it's resistive, right? So the equivalent circuit now becomes V7N, which we found to be 5 minus 3J, and Z7N is 1 ohms, right? And this whole thing now is connected to the 1 ohm. Right, so remember we were finding the equivalent circuit, Thevenin equivalent circuit from with respect to those two ports. So I put back the 1 ohm and then I have IO here. Here's where the 2 comes in. IO is going to just be V Thevenin over 2 ohms. So it's going to be 5 minus 3J over 2, which we've already calculated in the previous attempt and found to be 916. I think this is 916. Right? It's going to be 2.946 and minus 30.964. 2.916 minus 30 degrees. So yeah, so this is Norton's circuit, Norton's method, and we had to kind of do something to simplify the solution and get the Norton method quick, the equivalent circuit quickly. We could have done nodal analysis to get VOC, but it shows the fastest route. Okay. The final method we're going to do for this example is Norton's method. Right, and all you have to do here is again, let me redraw the circuit. I don't think I even need to look it up right now. So it's J, and then a current source, that's 2, 0, and then 6, 0 degrees, and then 1 ohms, IO, phasor, 1 minus J. Okay, so we want to find the Norton equivalent circuit. We have to turn the voltage, everything into current source, right? And so what we need to do is I need to take this out, and I need to find the Norton equivalent circuit. So this is the resistor, right here, and I will need to find the Norton equivalent circuit from looking into those two ports, those two nodes. Right, so what would be the Z Norton, and what would be the I Norton? Okay, to find I Norton, like that's let me remind you, if I have the Norton equivalent circuit and I have the impedance Z Norton in parallel, and this is I Norton, what I have to do to find I Norton is I have to short, right? Short the two nodes. So all I need to do is apply a short circuit and find the short circuit current, and that's gonna be I Norton, right? So that's it. What this does instantly when you short this, you cannot take this part of the circuit out. This part of the circuit is taken out because it's shorted, right? So what we end up with, this is I Norton. This is the shorted part, and then I have this voltage 6 0, and then I have this current 2 amps, and then I have J1, right? What's happening here is that I can use this voltage to find the current in this branch, and then the I Norton is just going to be the difference between this current and this current source, right? This current source splits into two at this node, right? And if I find this current, it's easy to me to find I Norton. I Norton is just going to be 2 amps minus this current. What's this current? This current is easy. It's minus 6, right? Because I need to find the current in this direction, but the voltage is negative, right? So minus 6 over the impedance, the voltage over the impedance, which is 1 plus J. So this becomes 2 plus 6 over 1 plus J, right? And I just need to calculate this. So it's going to be 2 plus 6, 1 plus J, 1 minus J over 1 minus J. I end up with 2 plus 6. This becomes over this is 1 squared plus 1 squared, 2, right? And this is 1 minus J. So this is 2 plus 3. 6 over 2 is 3, so 3 times 3J. So this is 5 minus 3J. Right? So remember, we always get this 5 minus 3J. So let me draw the Norton circuit. So this is IN, 5 minus 3J. And then the impedance. What's the Norton impedance? The Norton impedance, looking, right, to find the Norton impedance, I need to open this port and then find the equivalent impedance. The equivalent impedance is going to be just 1 plus J parallel 1 minus J. It's going to be 1 plus J parallel 1 minus J. We've already done this a million times. This is 2. Right? This turns out to be equal, sorry, not 2. We've done it here. This turns out to be 1 ohm. Right? So the Norton circuit, equivalent circuit, is going to be this in parallel with 1 ohm. It's only real, so it's only resistive. And those are the two nodes here. Right? So this is the equivalent circuit for everything here, except where we connect the 1 ohm here. Right? So I have to connect the 1 ohm, and this is IO. So using current divider, IO equals 1 ohm over this resistor over the total resistance, which is 1 plus 1, times IN. So this is 5 minus 3J over 2, which is equal, we've done this. Let me look it up again, 2.916 minus 30 something. 2.916 angle minus 30 something. Okay, now we want to do an example with a dependent source, which is something you also covered in circuits 1. So you covered how to deal with either current dependent sources or voltage dependent sources. So you could have a current source. You could have a current source that depends on voltage. So it depends on some voltage somewhere, or you could have it depend on some current somewhere. So you have a current. You could have a voltage dependent current source, voltage dependent current source, or a current dependent current source, or you could have a voltage dependent voltage source or a current dependent voltage source. So you have 4 different kinds of dependent sources. So we will do an example where we'll use the nodal technique, the loop analysis technique, Thevenin and Norton, right? However, when we typically deal with the circuits with dependent sources, we cannot in general use superposition or source exchange, because it gets a little bit more complicated. Because the idea of superposition is you remove, you kill voltage sources. The question arises is what portion of that voltage or current source that you killed transfers into something that appears on the dependent source. There's no way to exactly figure that out easily. That's why typically you cannot use superposition on a circuit with a dependent source, nor can you use source exchange. Excuse me, because typically source exchange is really another way, quick way of doing Norton and Thevenin, and you cannot do Norton and Thevenin quickly for circuits with a dependent source, right? You have to think about it a bit. That's why you should rather just use Thevenin or Norton right away rather than trying to quickly figure out the Norton and the Thevenin transformations on a circuit, rather than trying to figure out how to transfer a voltage source into a current source and vice versa. Okay, so yeah, so this is the circuit we want to analyze. Capacitor minus J, voltage of 0 volts, and then resistor 1 ohm, resistor 1 ohm. This is the dependent current Ix. We're measuring the current and using it for the dependent source, an actual current source, 4 amps. And then 1 ohms. Then we're measuring out this voltage, V out. It's a phasor, of course, because the sources are phasors. And then here is the dependent source. So this is a current source that depends on Ix, and it's 2Ix. And then finally there's an inductor here of J1 ohms. Okay. So we want to start with nodal analysis, and we have to name the nodes, of course, to do nodal analysis. So this is V1. I'll name this V2, this node. I'll name this V3. I'll name this V4. Notice there's a voltage source here, so V1 and V2 across this voltage source constitute a supernode. So we consider this to be one big node, and we apply KCL to it, meaning we sum all the output currents from this node. There are 5 currents coming out of this node. Right, and we just write the nodal equations. So we need to write the nodal equations, starting with the supernode. So starting with the supernode, I'll just write all the currents. Let me start with this current. So this is going to be V1 minus V2 over the impedance minus J. Then I'll do this current, which is minus 4, plus I'll do this current, which is V3 minus V2 over 1. And then I'll do this current, which is V3 minus, I call this V4, V3 minus V4 over 1. And then finally this current, which is plus V3 over J equals 0. Right? So this is this gives me, if I simplify this gives me the first. Oh, by the way, in this case V4 equals VO. if I solve for V4, I solve for the required VO. Okay, so this allows me to write down the first nodal equation. So I just gonna collect everything. So I want to collect everything with respect to V1. So V1 has only J, right? So I have J here. There's no other V1. And then the V2 terms. So V2 here, so minus J goes with the numerator becomes plus J, but there's a minus sign here. So I end up with minus J due to this thing. And then there's another V2 here. Yeah, there is minus 1. So I have a minus 1 minus J V2, and then the coefficient of V3. V3 I have 1 V3, 1 V3 here, so I have 2 V3. And then do I have an, yeah, and I have, oh, this is a V3. This is a minus J. I take J to the numerator, this becomes a minus J V3. Right, and then finally, the only term that's remaining is V4. So I have minus V4. Take 4 to the other side, I end up with 4. This is nodal equation number 1. Right. Then I want to look at node V2. At node V2, I have 3 currents leaving. So I have first V2 minus V1 over minus J. And then I have the second current leaving, which is this. So I have V2 over minus V3 over 1, and then I have minus 2Ix, the dependent source, equals 0. Now Ix is equal to what? Ix is this current, right? So that's equal to V3 minus V4 over 1. So that's equal to V3 minus V4 over 1. So I kind of collect everything. So V1 has a coefficient, again a coefficient of minus J. I took care of V1. V2 has a coefficient of plus J. I took J to the numerator here. And then I have 1 here, so plus 1. Right, 1 plus J. And then V3, so I have minus V3 here, and then minus 2V3, so it's minus 3V3, and then finally V4, I have minus 2 times minus 1 plus 2V4 equals 0. Remember the minus 2 here. Okay, so that's nodal equation number 2. Now I look at node V1, which is which node? Which is this node. No, not V1. Sorry, I look at node V4. So I covered the super node. I covered V2. Now I need to cover V4. This node. So this node has 3 currents going through it. So it has V4 minus V1. Well, first, forget about V4 minus V1. We have a current source. So we have 4 amps going out of it. So that's easy. That's the first current. The second current is going to be V4 minus, this current is going to be V4 minus V3 over 1. And then the third current is going to be V4 over 1, this current. This is a resistor, equals 0. So I end up, there's no V1, V2 here, but there's a V3, there's minus V3, and there's a V4 plus V4, so there's plus 2 V4, that equals minus 4, that's equation 3. And then the fourth, we have 4 unknowns, we need 4 equations. The fourth equation is going to be the constraint due to the supernode. So it's going to be V1 minus V3 equals 6, or equals 12, sorry. So the fourth equation is going to be the constraint equation due to the supernode. It's going to be V1 minus V3 equals 12. Right, and then yeah, so we have enough information to write the matrix that we want to solve. So we're solving for V1, V2, V3, V4. The outputs are starting with 4, 4, 0, minus 4, 12, 4, 0, minus 4, 12. And then looking at the equations, we can take the coefficients. So we have j minus 1 minus j, 2 minus j minus 1, and then minus j, 1 plus j, minus 3, 2, and then 0, 0, minus 1, 2, and then 1, 0, minus 1, 0. Right, the next step, so this matrix, we can call it y. This matrix, we can call it I, and then the next step is to find the inverse of this matrix. Right, so in this case, V1, V2, V3, V4 just equals the inverse of y times I, and that will give us the values. Right, so we can go to MATLAB and solve this. Right, so in MATLAB I entered the matrix y. Right, so I just entered it in matrix notation, and then I entered I, and then I just calculated V equals inverse yi. That gives me the voltages. What we're interested in is V4, which is V0 in our case. We find its magnitude, absolute. Its magnitude is 4 volts, and then its phase, which is angle, V, which gives me the angle in radians, the phase in radians. We divide it by pi, multiplied by 180 to get it in degrees. I get 143.13 degrees. So let me write that down and go back to my blackboard. The result of the calculation, and as we said, V4 equals V0, right? So it's the last one, last term. So V0 is going to be 143.1 degrees volt. Okay, so now we want to do the loop analysis. So we take our circuit and we recognize the loops in the circuit, and that's easy to do. Let me redraw this. Let me redraw the circuit. Right. So so if I redraw the circuit, let me check it out here. So you have dependent current source, capacitor, 2ix, capacitor minus j. I believe this is 1 ohm, 1 ohm, and then there is a voltage source here. I think it's positive, oriented in this direction. Yeah, it's positive, and it's 12. Right, and then there's a current source here, that's 4 amps. And what else? Oh, and then another resistor and inductor in the bottom. So we have a resistor and then inductor of J. Right, and this is it. And we're interested again in finding V out. And we want to use loop analysis in this case. So to use a loop analysis, we just identify the loops. It's easier just to do this. I1, I2, I3, I4, right? And just write down the loop equations. Apply KVL across all 4 loops, right? So let's start with the first loop. So this is the first loop going this way. Right? So we end up with what's the impedance of the cap? It's minus J, right? So it's always going to be the impedance times the current gives me the voltage in the KVL loop. So it's going to be minus J times I1, right? And then this is easy. I have a voltage source in the loop. So this is going to be, I'm going to meet the plus of the voltage source first when I go clockwise. So I'm going to have plus 12, right? And then I'm going to have plus I1 minus I3. In this branch, the current flowing is I1 minus I3. There are two loops passing on this branch, the I1 loop and the I3 loop. And because of the because we are going because we are going clockwise, it will be I1 minus I3 times what? Times 1. Right? 1, 2, 3, that's it, equals 0. So that allows me to write the first mesh equation, which is 1 minus j I1, right? Minus I3 equals minus 12. And then I do loop number 2. This is the I2 loop. I start from here. I meet the minus of the 12 first, so I end up with, this is 1. I end up with, I start with minus 12. Right? Oh, I don't have to do that even. This is simpler than I'm making it to be. I2 is just minus 4, clearly. We have a current source here. So I2 equals minus 4, and that's it. I can use this to reduce the number of equations, actually. So I2 is just minus 4, right? What about I3? Okay, now I3 is 2IX, clearly. But what's IX? IX, which is, let me see what direction IX is going. IX is going in that direction. So what's IX going in that direction? IX going in that direction is simply, this is I4 by the way, is simply I4 minus I2. So IX is going to be 2I4 minus I2, right? So this is simple really. So this is going to be 2 minus 2I2 plus 2I4. But I already know what I2 is, right? I2 is minus 4. So it's going to be minus 2 times minus 4. It's going to be 8 plus 2I4. So I'm going to end up with this equation. I3 minus 2I4 equals 8. That's equation number 3. Right? We don't really need to solve for I2. We only need 3 independent equations. We got equation 1, equation 3. We need now to get the final equation to solve I1, I3, and I4. Right? And once we solve I4, we know VO. VO is just I4 times 1, right? Times this resistor. Right? So let me look at this loop now, the I4 loop. So I end up with I4 minus I3. So I have I4 minus I3 times J. That's KVL. And then in the upper 1 ohm resistor here, what do I have? I have I4 minus I2. Right? So I have I4 minus I2 times 1. But I said I2 is minus 4, so this is going to be plus 4. Right? I'm just simplifying right away. And then finally, I4 1 ohm plus I4 1 ohms equals what? Equals 0. Okay, so let me collect I3. So I end up with minus J I3. And then let me collect I4. So for I4 I have a J here, and then I have a 1 here, right? And then I have another 1, so I have 2. 2 plus J, I4. That's it. So I collected the I4s and the I3s. All that's left is 4. I take it to the other side, equals minus 4. That's equation 4. Right. Now I can write a 3 by 3 matrix. Remember, I2, I don't have to solve for it. I only need to solve for I1, I3, and I4. So all I need to do is a 3 by 3 matrix. And I take the coefficients. So let me start from equation 1. I have 1 minus j, and then minus 1, and then minus 12. So 1 minus j I1, minus 1 I3, 1 minus j 0 minus 1, right? And then minus 12 on the other side. And then the second equation is trivial. The third equation gives me I3 minus I4. So 1 minus 2, 0, and then 8. And then the final equation gives me minus j, 2 plus j equals minus 4. This is the equation I need to solve. This is what? This is, let's call this Z matrix, and let's call this V, and we need to just solve for I1, I3, I4, noting that this equals Z inverse V. Let's go to MATLAB and solve this. All right, let me clear the command prompt, and then let's put in the matrices, right? So we have Z equals what? 1 minus j, we said, 0 minus 1. I do the next row now, 0, 1, minus 2, and then I do the third row, which is 0 minus j, 2 plus j. That's the matrix. And then V vector is going to be minus 12, next row, 8, next row, minus 4. Right, and then I is just going to be I1, I3, and I4 are just going to be what is they're going to be Z inverse Z times V. Let's now find its magnitude. See, I4 V0 we said is just I4 times 1, so I got a 1, so that tells me that I plugged everything correctly. I didn't get a different result. And then take the angle of my solution divided by multiplied by 180, 143.1. So we get exactly the same result. Let me go back. Right, so going back, what we found out from the solution, I don't care about I1 and I3, but I found that I4 equals, it's the same value that we got up here. So we got this 143.1. So it was 4 angle 143.1 degrees amp. So VO is going to be this current times 1 ohm. It's just going to be 143.1 volt. Okay. The next step is finding the Thevenin, using the Norton and Thevenin techniques to solve this problem. So we will do that next. Analysis now. So we want to try find the Thevenin equivalent circuit technique. So let me redraw the circuit. So 2IX, 12 volt phasor, 1 minus J, 1, right? And what we do now is, instead of the 1 ohm resistor, we want to take the 1 ohm resistor out, and we want to find the equivalent resistor, the equivalent Thevenin circuit for this whole circuit, right? So what we want to do, we want to find the V Thevenin and the Z7. And to find the V7 is just the open circuit voltage that appears here, right? We can find this easily. This is Ix. How do we find this? Well, we know that V7 is the voltage drop across this resistor, right? Is the voltage drop across the inductor minus the voltage drop across this resistor from KVL, right? But we know what the voltage drop is across this. We know what's the current that's passing through the inductor. What is the current passing through the inductor? This is open, right? So the current here is 0, and the current here is 0 because this is open. So the current passing through the inductor is just 2Ix, right? This current here. You see that, right? So the voltage drop across the inductor is going to be 2Ix J minus the voltage drop across the resistor, which is going to be minus. What is it going to be? Well, what's the current passing through this resistor? It is 4 amps, right? It's this current. All the current is passing through that resistor, so it's going to be 4 times 1. Right? So, but we know also Ix is 4, right, in this case. So we end up with V7 equals 2, 4, which is 8. So it's 8J. And then we have a minus 4 volts. So this is V7, right? We want to now find Z7. There are many ways to find Z7. We could, like in the book, I would suggest you look at that. In the book, they kill the sources, and then they apply a test voltage source and calculate the current, and then when they divide the test voltage source by the current that they calculate, they get the Z7. And we could also short this and find, like if I have an equivalent circuit and I just short the outputs and I calculate the I short, V7 over I short is going to be just Z7, right? Clearly. I'm going to use that technique instead. So I'm going to just, I want to do the same circuit, but I want to now short, right? So this is now shorted. Right? And this requires us to do some mesh or nodal analysis. Again, we have freedom to do whatever we want. There are many roads that take us to Rome. There is not a single technique. There's no unique technique that we have to use. Right? We can use multiple techniques. So this is Ix. I'll use because it's simpler. It only requires solving 3 equations. I'll use mesh or loop analysis. So I have I1, I2, I3, I4, and then I short circuit is just going to be I4, clearly. Okay, so let's get the first mesh equation, starting with the I1 loop. So I have minus J I1 plus 12 plus I1 minus I3 times 1 equals 0. And I'm positioned to write my first equation. So I have 1 minus J minus I3 equals minus 12. That's the first nodal equation. Second nodal equation, well, it's not an equation, it's just I2 equals minus 4. It's easy. So I2 is known, already solved. The third nodal equation is I get it from the I3 loop. I know that I3 equals what? 2Ix. But what's Ix? Ix is here, right? Ix is just I4 minus I2. So Ix is, so this equals 2I4 minus I2, but I2 is minus 4, right? So this is going to be plus 4. Right? So I end up with I3, take I4 to the other side, minus 2I4 equals 8. This is the second mesh equation. Right? The third mesh equation is from I4, the I4 loop. So I have Ij, I have J, the inductor, and I have I4 minus I3 plus I4 minus 4, right? I4 minus I2, I2 is minus 4, so it's going to be I4 plus 4 times 1 equals 0. So I take the I3 out, I end up with minus J I3, and then I have 1 plus J I4 equals minus 4. That's equation number 3. That's it. And now I just construct my matrix system. So I have 1 minus J, minus 1, 0, 0, 1, minus 2. Those are the coefficients. And then 0, minus J, 1 plus J, and I'm solving for I1, I3, I4, right? And this equals minus 12, 8, minus 4. This is the Z matrix. This is the V matrix, and all I have to do now is to go to MATLAB to solve this. Alright, so I already plugged the matrices in previously, so let me take them back in. So Z, this is the matrix, right? Right, so this is gonna be minus J, and so this is the correct matrix, and then after that I put in the V vector, and then I solve for I. Okay, so this is this is the last one is I4, right? So what was, let me see. So I did the calculation here. This is V Thevenin. This V Thevenin is what Z Thevenin is 1 minus J. Right? Z Thevenin is just going to be V Thevenin over I short. I short turned out to be minus 6 plus J2. Okay, so let me go back to my board. What we calculated was that I short, which is I4, that's all I care about, was minus 6 plus J2. So Z Thevenin is going to be V Thevenin over I short circuit, which is going to be minus 4 plus J8 over minus 6 plus J2. This equals 1 minus J. So this is the Thevenin equivalent circuit. It's going to be minus 4 plus J8 volts. Then I have the Thevenin impedance, which is 1 minus J. I can draw this as a resistor and a cap, right? A cap has minus J, has a negative reactance, but that's fine. I can just represent it as a box. That's fine too. And then 1 ohms. Right? Now, what is VO? VO is just a voltage divider in this case, simple voltage divider. It becomes 1 over 1 plus 1 minus J. It's 1 over the total impedance times minus 4 plus J8. So this equals minus 4 plus J8 over 2 minus J, which equals minus 3.2 plus J 2.4. If I turn this into polar form, I'll end up with 4. 143.13. Exactly the same result. Okay, so this is Thevenin. The last thing we want to do now is Norton's theorem to finish this example. Well, I mean, we've already done all the work to do Norton's theorem. What do we need to do Norton's theorem? We need to find the short circuit. Right, I Norton is the short circuit current. We already found that. up here minus 6 plus J2. So I Norton is minus 6 plus J2 is short circuit current. It's the current that you get if you short the terminal. You are finding the Norton equivalent circuit through, right? And yeah, what's left is the Z impedance, Z Norton, and Z Norton is really equal to Z Thevenin. Right, to show that, I mean, look at this scenario. In this Norton equivalent circuit, what would Z Norton be? Z Norton be, let's assume you leave the terminals open, so you have some VOC. Z Norton is going to be just, right? So I Norton times Zn equals VOC, right? So Z Norton is just going to be VOC over I Norton, that's it. But we already calculated VOC when we calculated the Thevenin voltage. VOC is just the Thevenin voltage, which is minus 4 plus J8. So minus 4 plus J8 over I Norton. Right? This is the Norton. It's V open circuit, which we already calculated, which is equal to V Thevenin. And then I Norton is equal to the I short circuit, which we already calculated. It's going to be minus 6 plus J2, right? But that's exactly equal to Z Thevenin, right? Minus 4 plus J8 over minus 6 plus J2. That's exactly equal to Z Thevenin. So Z Norton, the Norton impedance and the Thevenin impedance are exactly equal, and you can see that. So this is 1 minus J. So this would be the Norton equivalent circuit. I would have minus 6 plus J2, and then I would have a 1 minus J impedance, right? And then all I have to do now is add the resistor, 1 ohms. Okay. Now I want to find VO. One way to do that is to find the equivalent impedance of those two impedances. So I need to simplify this to minus 6 plus J2, and then I need to find this impedance. I need to find 1 minus J parallel 1. What's this impedance? This is going to be 1 minus J times 1 over 1 minus J plus 1. So it's going to be equal to 1 minus J over 2 minus J, right? Which is equal to 1 minus J 2 plus J over 2 plus J, 2 minus J. That's going to be 2 squared 4 plus 1, which is 5, right? So I'm going to end up with 2 plus minus J times J1, this is 3, right? And then this is the real part, and then the imaginary part is minus 2J plus 1J, which is minus J over 5, right? So what is this? This is that impedance. So what is VO? VO is just going to be this impedance, equivalent impedance, times the Norton current. So this is going to be minus 6 plus J2. Let me go and use MATLAB as a calculator to calculate this. All right, let me clear the screen, and then I just want to use MATLAB as a calculator. That's it. So 3 minus J divided by 5 multiply by minus 6 plus 2J, right? That's all it is. Let me call this VO. Right, it's a result, and absolute VO is going to be 4, exactly what I expected. And then the angle of VO in degrees is going to be angle. It's going to be, as I expected, 143.13 degrees. Writing that down, VO is equal to 4 143.13 degrees, the exact same result. Okay, so it's a long example, but it's a good review of all the techniques that you've learned and mastered in circuits 1. Hopefully with more homework and more practice, you will sharpen those skills. All right, thank you guys.